Hello, this is Dean Radin. My talk is an entropic anomaly in 23 years of truly random data. Yoda told us that he felt a disturbance in the force. The question that arises is this just an interesting storyline, or is it a useful clue about the nature of mind and matter? Well, there's several theories about mind and matter. The first one is the dogma within neurosciences today. It's you're nothing but a pack of neurons from Francis Crick, or you're a machine made of meat from Marvin Minsky. This is the scientific worldview, reductive materialism. It's very effective. Second theory, consciousness is fundamental, said by Max Planck, among many, many others. This is idealism, the esoteric worldview. The third theory is that it's not really materialism or idealism, but something else, something emerging from something more fundamental, such as Carl Jung's idea of an unus mundus, a third source. So in this idea, which is sometimes called dual aspect monism, the two aspects are mind and matter, but it's monistic because they're not separable and they come from somewhere else. Well, we don't know where the somewhere else is, but mind and matter are both real things, but like two sides of the same coin, fundamental and connected in an intimate way. So if you look at philosophy, you'll find people like Spinoza and Russell and James and Mach talking about various versions of dual aspect monism. If that idea is true, then when there is mental order, it may be correlated with physical order in the environment. And likewise, mental chaos would be correlated with physical chaos or disorder. The test if this is true, we need a material target system that's impervious to mundane influences and appears to be susceptible to variations in human attention or intention. Well, that's a random number generator that's been used for over half a century now for these kinds of experiments. In the field consciousness sense, we use a random generator to produce streams of random bits that produces well-behaved noise, which in turn can be used to measure entropy, which can be visualized in terms of the shape of a normal curve. So this is sometimes why I think of this as a field consciousness experiment is looking at for whom the bell tolls, except in this case, it's a normal curve bell, a bell-shaped curve. You're probably familiar with the Global Consciousness Project, which places random number generators around the world, running continuously. This was the brainchild of Roger Nelson. And every 5 minutes, they send samples of randomness up to a central server at Princeton. It is certainly the case that in a collective sense that a lot of people are using their attention and intention to try to do something in the world. We see it in this context, we see it there, we see it here. This is a very popular thing for people to do. The question is it doing anything or is it just making us feel good? Well, the Global Consciousness Project is trying to figure this out. And so as a metaphor, we can see the project as a kind of tsunami detection system, except that these are random generators floating on an ocean of consciousness rather than an ocean of water. So here we have a random generator metaphor. If there are spatial and temporal correlations arising among many buoys in the ocean, we call it a tsunami. If this is happening, and there's an illustration of a tsunami, the effect of it, if this is happening in the ocean, we can detect it as ripples in the structure of the space-time itself of the ocean. And something like this as a metaphor is what we think is going on, or at least what is planned to go on with the Global Consciousness Project. So here's the famous case of 9/11, where we look at the random walk that's being produced by the random generators up to September 11th, and then there's a very significant deviation that persisted for days afterwards. So it's random before, apparently not random during and afterwards. So this is a little bit like a tsunami event. When you look at the overall experiment of the 500 formal tests, it ended up with a 7 sigma result. So this presents an anomaly. The question is, how do we explain this anomaly? Well, before I get into that, I also want to mention that one of the other things that we looked at on September 11th was a possibility of an autocorrelation that arose in the data that persisted for over 2 hours, and actually even longer than that, but very significant autocorrelation, which means there is temporal structure that arose during this event for hours afterwards, as compared to other days where the same analysis is used and you don't see temporal structure. So here's, imagine this is the random walk produced by the random number generators. What we see in the data is something like this. A deviation occurs at the time that there are events. So most of the time it looks like a random walk, but was the 7 sigma deviation overall due to influence by countless groups of people around the world or by selection of events to analyze? Because after all, if you had selected other events, other deviations, that eventually would have resulted in a 7 sigma result as well. So the boy is asking, do you mean that the experimenters intuitively selected events that would deviate? Kind of like this cartoon says. Or as Bernie is asking us, are we talking about consciousness as caused or causal? He's asking, did Roger Nelson get a 7 sigma result in an experiment simply by guessing the right time to select events? Here's another illustration of a random walk. Is this deviation here meaningful? Is that meaningful? Well, one way to approach this question is to think of this as a complex signal which we decompose using Fourier transforms. So maybe this signal here, I'm putting signal in quotes, is a worldwide meditation for peace. And this one is a tsunami in the Philippines. And this is a rock concert. And this is just a person playing with their dog. So maybe what we see as a random walk is the combination or convolution of many, many influences out there that consciousness is somehow engaged with. The data from the GCP is in the form of a daily matrix. It has each second over the course of a day, and it has time synchronized random number generators running that day. So originally started with 3, went up to about 70 at the peak, and currently is still running with about 20 generators per day. You take all that data per second and you combine the z-scores, you create z-scores and combine them into a Stouffer z. So you have one array over the course of the day, which reflects the behavior of all of the random generators over the day. A little bit like our combining our results of many buoys to look at the results. So one sample for each generator is a sum of 200 bits. The sample is checked to make sure it's within a sane area. It has to be greater than 55 and less than 145. These are both 6 sigma outliers. We normalize the daily sample so that the z-score in each one of these little boxes is the data, the sample, minus the mean of that random generator divided by the standard deviation of that generator per day. The daily z array, meaning this array, the final array, has to pass a Wald-Wolfowitz runs test above 0.05 level. We require a minimum of 3,600 z-scores or 1 hour's worth of data per random generator per day. We exclude random generators that have outlier means. And so we look at every random generator per day and its mean per day, and sometimes they don't behave very well. So if that is happening with a random generator for reasons we don't know, we exclude it from the further analysis because it would act as a bias. And then we consolidate these seconds into 1-minute segments. So we collapse a 6,400 data points into 1440, one per minute. For control data, we randomly scramble the sequential order of each of the daily z-scores per minute. And then we pass the original and scramble arrays through 4 additional randomness tests. In each case, when we do this, we're trying to get rid of outliers, essentially. So the 4 tests are a sequential runs test, a second kind of sequential runs test, a third kind of sequential runs test, and a Lilliefors normal distribution test. So we're looking at both how the data are distributed in distribution overall, and also how it is distributed temporally. Both the original array and the control arrays have to pass all of these tests at above 0.05 to be included in the rest of the analysis. And then we apply something called multiscale entropy analysis. This is very popular now, used in lots of different contexts. The curve that results from this analysis compares the relative complexity of normalized time series, and it reveals structure with long-range correlations on multiple spatial and temporal scales. So it's a perfect kind of analysis to use for the GCP data. So here's an example. If you have a signal that is 1 over F-type noise, you get a flat curve with this analysis. If you have white noise, which is what a random generator produces, you get this declining curve. So as we go down in this graph, we're dealing with simpler signals, low entropy, ordered for patterns, and it is compressible from an informational perspective, and the exact opposite if the curve is going up. So here's just a couple of examples: a healthy heart, congestive heart failure, atrial fibrillation. These are the actual values of what you get when you, with these different conditions. And this is what you get when you apply multiscale entropy to these different signals. And you can see then that the nature of the signal produces a different pattern in this method. So what we do here is take the multiscale analysis, entropy analysis for week-long samples. So it's 1440 minutes per day times 7 days, or 10,000 minutes that are applied to multiscale entropy analysis. And it looks like this. It's very much like white noise, like we would expect, except that this signal actually consists of 3 things that are overlapped. The black is the GCP data, the red is the same data scrambled and sequentially scrambled, and then the green, which you can't see here, is pseudo-random data. So we can look at this in a little more detail. So here's the same scale, except we're going to blow up this figure here to see what's going on at scale 15. And as you see then, here's the original GCP data over the course of a week. And this is the same data scrambled and the same data just looking at random data. These are 95% confidence intervals, so you can see at a glance that there is a difference here. And the GCP data is more negentropic as compared to random or scrambled data. So this is yet another way of looking at it. This is now 2 weeks of data, so 20,000 samples. I use these kinds of analyses for the rest of this analysis here, using a fortnight of per minute data. And so if you look at the scale over a long period of time, this is from 1 minute up to 60-minute segments, the GCP data versus the same data scrambled to destroy the temporal sequence, clearly this is negentropic. And these dots here are representative of a false discovery rate to adjust for multiple analyses at the 0.001 level. So all of these points here are significant, at least at 0.001. And by comparison, original GCP data that is scrambled versus pseudo-random data, in which case you get nothing. So it's indicative of some kind of temporal structure that appears to arise in the real GCP data. You can do another kind of analysis called complexity index, where you take the area under the curve. And now it lets you easily compare effect sizes in different conditions. So here we have the real GCP data versus scrambled, real GCP data versus random, and scrambled versus random. So this is pretty much what you would expect if the GCP data really did have a temporal structure to it. It shows structure compared to its own data, temporally scrambled, versus random data, and the random versus scrambled is nothing. You can look at this in other ways too. These are the data that passed the randomness tests versus did not pass the randomness tests. First 6 months of the year, second 6 months of the year, even data, odd data, events that were looked at in the GCP versus events that were not looked at. So in all of these cases, even with different partitions of the data, you're seeing that the real data actually does have some kind of structure to it. So there's some structure in the GCP data. If this is true, then the peaks and the troughs And what looks like a random walk may not be purely random. And so we get asked, like in this question, and do you see the butterfly? Well, this, of course, is a magic eye image. If you were looking at this in the right way, you would see a butterfly pop out. And so maybe if we look at a random walk in the right way, we would see structure that otherwise we would not see. So here is another random walk. We will create a threshold to determine what we consider to be peaks and troughs. This will allow us to select out both positive deviations and negative deviations. What we will do with this is, let's assume then that this is one of our segments. And we'll put it into 8-minute segments. So we have 180 8-minute segments per day. And we do this for each day. And we turn this into a circular shift so that we take whatever the peak is and we put it in the center. And we take that peak and put that in the center, this peak in this center. This is just an illustration for positive peaks, but we do the same for negative peaks. You then create an ensemble average. So for positive going peaks, it's not surprising that you would get an average that looks like this, where our threshold is 3.5 z-score. And so you're going to get a very large spike right in the middle, and everything else looks more or less flat. But if this spike is caused, in quotes, by a shift in collective attention, then there may be a non-random structure that is actually arising before and after the peak that we can't see because the scale doesn't allow us to see it very well. So maybe we get something that kind of looks like this. If this spike is completely random, then data near the spike shouldn't show any structure at all. So we do an analysis where we take out that middle spike and we see what's left. So for the negative going spike or the data, it actually looks like this. And for positive going, it looks like this. If you take the difference, it looks like this. Now the question is, this happens to be for 12-minute daily segments. Is this rise significant? Because at this point, looking at it like this, you can't really tell whether this is a significant deviation or not. So to figure it out, we do a permutation analysis where we take the original data, we randomly permute it, and we repeat this 1,000 times to figure out what does the original data look like as compared to permuted data. And so for 15-minute segments with thresholds for peaks and troughs at a z-score of 3.5 or negative 3.5, you get a result that looks like this. Now we can create a joint p-value for both two things. One is the distance of the maximum z-score from the middle point, which is where the spike used to be, and also the height of the curve at that point. So you take the probabilities associated with these two and multiply it. And so the joint probability of this particular result is, as you see. For 12-minute segments, it's much stronger because the peak and the distance happen to be exactly at the center point. We can do the same for 10 minutes. We can do the same for 8 minutes. And again, we're seeing interesting deviations around this center point. Well, what about, here's the first peak and trough. What about the second one or the other ones? Are these caused or are these random? So we rerun our analysis using the second maximum, the second minimum, third and fourth, and so on. Do we see similar temporal dependencies showing up? And the answer is yes. So this is for 12-minute segments. We're using a maximum and minimum peaks and troughs from 0, which was the original analysis, up through the 6th largest and the 6th smallest. And you see the same shape, suggesting that additional evidence that there's a convolution going on, that what looks like a random walk is not quite random as we thought. We could also then do partitions of the data. So for example, even and odd days, we get similar shapes, stronger for odd days for some reason. And again, for last 6 months of the year, first 6 months of the year, again, similar shapes. So the implications of all this, as Einstein said, that God does not play dice with the universe. Maybe there are no random walks. But in this case, then, Robin is asking Batman, then who's playing dice? And Batman says, well, we are. Well, in this context, consciousness apparently, maybe, is playing dice with the universe. or more like this, that what to us would seem like a chance event, maybe something else is going on. Of course, this immediately also raises important questions about free will versus determinism. As Isaac Singer once said, I believe in free will, I have no choice. I have to believe in it. So this is a complex issue, but it kind of is in this direction of maybe not determined. Maybe free will is involved in pushing the universe around in such a way that when we see what looks like a random event, may not be quite as random as we thought. So I'm going to end there, and I thank you for your kind attention.